Section 12 is about alternating currents, which I'd kind of sort of gotten involved with at the end of section 11 in an LC circuit where the charge is going back and forth, oscillating. That's an alternating current. The RC circuits and the LR circuits, those were direct current because the current always flows in the same direction. The LC circuit, that was sort of a little warm up for section 12. So household electricity is an alternating current. The signals in some audio system would qualify as a type of alternating current with a much higher frequency than what you have in, for power distribution, the electric company. But let's talk about just plain. I mean, you get into sound systems, and you can have much more complicated waveforms than this. But what the electric company sells you is just a nice, simple. Well, I mean, it might be a few little spikes on it here and there, but basically, it's just a nice, simple sine or cosine wave, depending on what time you start your clock. Let's say the current is a sine, okay, so that it goes up through 0 at time equals 0. As I pointed out at the end of section 11, when I was talking about the LC circuits, the volts and the amps do not necessarily have to be in step with each other. I pointed out how in that particular situation, one was a sine while the other one was a cosine. So in general, there could be some phase angle phi anywhere between plus 90 degrees and negative 90 degrees. That's the phase difference between the amps and the volts, okay? So in general, the one curve would be shifted relative to the other, the volts shifted relative to the amps by an amount that depends on the phase angle, like that. And omega, of course, equals 2 pi f, like we've encountered more than once before. So these will be the general equations for how current and voltage vary with time. When people talk about household current being 120 volts, what does that mean? Or if they talk about how many amps, that you've got a wire leading to a lamp, and somebody says there's 1 amp flowing through that wire going to that light bulb. Well, what does it mean if you've got 1 amp of alternating current? Because, of course, it isn't 1 amp all the time like it would be with direct current. It's actually constantly changing, like this graph here. So maybe I'll start out with what it's not. First of all, 1 amp is not the average current. If you look at this, it's positive half the time, it's negative half the time. The negative part is symmetrical with the positive part. And if you average it all out, it's 0, okay? Which is what happens if you hook up a DC meter in an AC circuit. The needle tries to keep up, but the meter movement has too much inertia. It can't really move that fast. And the needle just sits in front of 0 and kind of tries to quiver, like it's having some sort of seizure or something like that. So average current is 0. That's not what the 1 amp of AC means. Another thing that it is not is the amplitude, okay? This max, if you've got a meter spliced into a circuit and it reads 1.00 amps, this maximum current that you'd have on the graph here is actually a little more than 1.4 amps. So that's not what this means either. Rather, what that does mean is it's the effective current, as in how many amps of direct current would deliver the same power. If you got 10 car batteries and hooked them up in series so that you had 120 volts of direct current just like your 120 volts of house current, and you hooked your lamp up to that, and 1 amp is going up the cord, okay, that variable voltage, or that variable current that you get from your household outlet would make the bulb exactly as bright as if you had a steady 1 amp of DC. It would, it would make the toast just as brown in the same amount of time. If you had a space heater, it would keep you just as warm. In other words, it delivers the same power. Now, power depends actually on I squared, not on I. Okay, from fairly close to the beginning of the course, power delivered by an electric current is equal to I squared times R. So really, it's if you want to talk about the average power being delivered, the average power depends on the average value of I squared, not on the average value of I. That's kind of what I wrote down here. I is equal to, if you take this function for I and you square it, you're going to have the amplitude squared. Incidentally, footnote, if anybody's wondering about my use of capital letters and lowercase letters, well, this actually is more time to explain than it's worth, but what I was doing is capital letters are things that are constants. I max, the amplitude of the current, that's a number. Lowercase letters are for things that are functions of time, okay? Little I changes with time according to this pattern here. So anyhow, the average value of I squared would be the square of this function, I squared times the sine squared, the average of that. Well, a constant squared, the average value of pi is pi. It's not too hard to average a constant. As for averaging the sine, well, probably doesn't hurt if I sketch a picture of it. I've got a picture here of what the graph of the sine looks like, but the sine squared looks something kind of like that. Because when you square it, you lose all the minus signs, okay? So the sine squared goes back and forth between 0 and 1, and just looking at my crude little sketch there, you might guess that the average value for that function is 1/2, and actually to prove that, instead of just saying, "Ooh, that's what it looks like," consider the Pythagorean trig identity. Sine squared plus cosine squared equals 1. Well, if sine squared plus cosine squared equals 1, then it must be that the average of those things add up to 1 also. I mean, if this is always equal to 1, it's going to be equal to 1 on average. The thing is that the sine squared and the cosine squared have the same average, because this was sine squared. But if the origin had been over here, so that the y-axis was here instead of there, it would be the cosine squared. Sine squared and cosine squared, it drives math majors crazy when I say things like this, but sine squared and cosine squared are the same function, really. It's just one has been slid across the picture a quarter of a cycle compared to the other, okay? So sine squared plus sine squared average equals 1, which you can combine those two terms. So the point is that the average value of the sine squared is 1/2, kind of like I put on my little sketch there. So filling in a 1/2 for the average, Gotta slide that up. Filling in a 1/2 for the average value of sine squared, right there where the sine squared used to be. I've got the Imax squared times the average value of the sine squared times R. Well, the power is equal to the square of the effective current. You know, if it was DC, it would just be power equals I squared times R. That equivalent DC voltage squared times R is equal to the power. And we can see here that that relates to the amplitude of the current, you know, the peak current, where it's right up here at the top. I squared effective equals I max squared times 1/2. But nobody wants to talk about square amps. So take the square root, and the effective voltage, often called the RMS it's current. Voltage behaves the same way, but the effective current, often called the RMS current, would be equal to the peak current divided by square root of 2. So that's, you know, square root of 2 is around 1.4. So that's what I meant when I said that if you have 1 amp in a wire, this graph actually peaks out at about 1.4 amps, 1.41 amps, if you want to get a little more precise about it. RMS stands for root mean square, which I should probably explain a little bit. But first of all, I wrote down in the note packet there, I don't quite remember why I wrote down one and not the other anymore, but the root mean squared current is the maximum current over the square root of 2, like it says in the printed version over there. Likewise, voltage, it's exactly the same story. Because if you calculate, you can also calculate power from V squared over R. So just as power depends on the square of the current, power also depends on the square of the voltage. So it's the average value of V squared that matters. And it's the same story all over again, which is why I accidentally said voltage once or twice when I was going through it. So for example, when somebody tells you there's 120 volts in a household outlet, if you actually were to draw the graph of you know, the voltage as a function of time, the amplitude is actually about 170 volts in a household outlet. 170 divided by the square root of 2 is the approximately 170, 171, something like that. That's when you divide by the square root of 2, that's the 120 volts everybody talks about. Okay. In physics textbooks, sometimes people talk about the maximum current and the maximum voltage. Sometimes that's convenient. Like when we do the lab for this part, you're going to be reading voltages off an oscilloscope. Well, you know, it's a lot easier to read where that thing peaks out than to try and figure out where the peak divided by the square root of 2 is. You have to calculate that. You can look at it and see the amplitude. So there are times that you want to talk about what is the maximum voltage. But, you know, as far as going over to Home Depot and buying some circuit breakers or some wire or something like that, if somebody tells you that a circuit breaker is going to trip at 15 amps, that's the root mean squared current, not the peak. Okay. And if you know, if you talk about house current being 120 volts, that's root mean squared, and so on. If you get a meter, an AC meter, and you read AC amps or AC volts, that's RMS. So once you get away from some sort of highbrow course about this stuff and get out to where you're actually just, you know, running, fishing wires through walls or soldering something, it's always root mean squared that people talk about. They talk about the effective voltage and current. But what exactly does it mean? Root mean square. Root mean square. That's what RMS stands for. It's another kind of average. Usually when somebody talks about an average, it means an arithmetic mean, okay? It means, like if you're calculating the average grade on a test, the mean is when you add up all the grades and divide by how many people took the test, okay? A root mean square is a different kind of average, a slightly longer procedure. First you square, and then you average the squares, and then you take the square root again. So it's a little more elaborate when you're doing it to a function, but just to illustrate the idea with just a couple of numbers. Let's say we wanted to know the average of 3 and -3. Well, you know, a mean, a regular average, as I said a minute ago, the procedure is you add the numbers, 3 plus -3, and then you divide by how many numbers there are. The average of those two numbers is 0, but if you do an RMS, first you square. 3 squared is 9. -3 squared is also 9. Then average the squares. So you add them and divide by 2 because there's two numbers in the set. Then take the square root. Square root of 9 is 3. But before everybody gets the idea that an RMS just means average the absolute values, no, actually, let's run through another example. What if the numbers are 1 and 5? So, same as before, to average them, 1 plus 5 over 2, the average is 3, just like it was with the other example. Okay, add the numbers, divide by how many numbers? For a root mean squared, first square the numbers. 1 squared is 1, 5 squared is 25. Then average the squares. Okay, I've got two numbers in the set, so you add them and then divide by 2. 26 divided by 2 is 13. And then you take the square root. Square root of 13 is definitely not equal to 3. If you round it off a little bit, it's around 3.6. Okay, when you do an RMS, it gives more weight to the larger numbers than what happens with just a regular mean. It's a useful thing. It's an appropriate thing to do anytime that it's the square of the variable, because, you know, you're looking at the average of the squared value. If it's the squared value that matters, an RMS is an appropriate thing to be talking about. Another place that it comes up, aside from, talking about AC voltages and currents, is when you get into the kinetic theory of gases. Quite often people talk about the RMS speed of, say, we're talking about the air in this room. The reason you might be interested in the root mean squared speed, which is faster than just the mean speed, is because the temperature of the gas depends on the average kinetic energy of the molecules. And the kinetic energy is 1/2 mv squared. So it's the average value of V squared that determines the temperature of the gas, which makes a root mean squared an appropriate thing to look at in that situation also. So anyhow, back to the outline here. I will explain exactly what is meant by a root mean squared. I just did that. And I also already said that meters and a variety of other things, when somebody tells you that 14 gauge wire can carry 15 amps, they're talking about the root mean squared current. Okay, so for any kind of practical electricity, whether you're reading numbers off a meter or whatever, it's almost always the effective value, not the peak value. So a little problem to solve before we dig ourselves into this any deeper. A household outlet well, not only in the United States, as I understand it, anywhere in North America, the standard is 120 volts. But yeah, the electric company doesn't have to be too particular about that. It's not worth a lot of fuss. If you've got 117 volts at your house, and if we've got 121 volts in the physics lab at the college, it's all good. Just about any kind of electronic product that you can buy is designed to operate. I think they'll go as low as 105 volts before you're really got any risk of hurting anything. And I think you can go at least as high as 130 and get away with it, maybe even 135. So getting exactly the right voltage is not much of an issue. On the other hand, I think I mentioned this when I was doing Lab 8, when that was the one with the oscilloscope where we were comparing the signals. This one's 60 hertz and matching it up and got the circle on the oscilloscope screen and all of that. I think I mentioned then, they have to be very careful about getting exactly the right frequency, because if you've got one power plant that's running at 59.9 hertz and another power plant that's running at 60.1 hertz, and you dump all that electricity in the same grid, you're going to get beats. Okay, you remember beats from Physics 131? That's when the amplitude goes, wow. I was demonstrating it with sound waves back then. Wow, wow, wow. You get constructive and then destructive and then constructive and then destructive interference. And that would be bad. Okay, so 60 hertz on the dot. And let's say at this particular house, it's 121 volts you've actually got instead of the 120 that's the target. So from those numbers, basically all it's asking you to do is go up here to the top of the page, and assuming that the phase angle is 0, it says that in the question, just fill in for numbers for everything to the right of the equals except for t, so that you've got the voltage as a function of time. Basically, you have to figure out Vmax and you have to figure out omega, and that's all there is to answering that question. So section 12, number 1. So the general form, and I'm pretty sure it's on your formula sheet somewhere too, is that the voltage is equal to the peak voltage. Maybe I'll just put M instead of writing out max, abbreviate the abbreviation. So you look at the formula sheet, it says that. You look at the question, it says assume that the phase angle is 0 in this case. Omega is 2 pi f. Radians per second, cycles per second, 2 pi cycles per, I'm sorry, other way around, 2 pi radians per cycle, or 2 pi radians per revolution, if you'd rather say it that way. The number of revolutions per second that the generators are spinning, that'll be the number of cycles per second of the alternating current that it's producing. 60 hertz for the frequency, and well, if you want to be exact about it, like you would in a math class, (120 pi radians per second is the angular frequency. If you don't want to be quite so exact, that 120 times pi is around 377. As for the amplitude, no, don't put the 120 volts in there. What have I said that like 5 or 10 times in the last few minutes? Maximum divided by the square root of 2 is RMS, is the way it says it in the note packet, and I think I probably wrote it the same way on the formula sheet. Well, since the maximum is what we're after, got to rearrange it. So it was 121 volts. And that comes out 171 after you've multiplied by the square root of 2. Putting it all together into the function that the question asked for, labeling the units and everything, which is something I quite often skip, but you want to keep in mind that the units are in fact there, even if somebody gets lazy and doesn't write it down. The amplitude would be in volts, 171 volts. And the frequency is in radians per second. So that means the time has to be in seconds, and after you've multiplied, the calculator has to be in radian mode. Okay, so that's a general introduction to a little bit of what's going on with an alternating current. Let's look specifically at what happens when an alternating current goes through a resistor, a capacitor, or an inductor. I started with resistors because that, I suppose, the simplest case, takes the least explaining. Two questions I want to address in each case. First of all, if you've got a resistor and you apply a certain number of volts, how do you figure out how many amps results? Well, for a resistor, that's just Ohm's law. Well, to be precise, Ohm's law applies to the DC voltages, okay? You shouldn't automatically assume that everything I said about direct current automatically carries over to alternating currents. For example, Kirchhoff's loop rule says that if you add up all the voltages around a closed loop, they have to add up to 0. Well, AC voltages are always positive. Okay, there's no way to get a negative number out of a root mean square. And there's no way you're going to get a bunch of positive numbers to add up to 0. So Kirchhoff's loop rule is invalid for AC voltages. So you shouldn't necessarily assume that everything that we said about DC carries over. The instantaneous voltages are basically DC voltages because, you know, if you're looking at a really short time interval, okay, here's the graph again. You've got either the current or the voltage, either one you want to talk about, kind of changing sort of like that. And if you look at a time interval from like there to there, or it doesn't matter where you do it, you know, basically from there to there, as that time, this is time on the horizontal axis here, as that time interval approaches zero, that current or voltage isn't really going to change any significant amount. So when you talk about an instantaneous value, then yes, during some vanishingly small time interval, you have direct current. And so the instantaneous values do obey everything I said about direct currents earlier in the course, including Ohm's law. So the instantaneous voltage equals the instantaneous current. I'm off the bottom of the picture. The instantaneous voltage equals the instantaneous current times the resistance. And that's established back in the DC part of the course. Well, if this is equal to that at every single instant, then this is going to be equal to that on average. It's like if you've got two students sitting next to each other and they always get the same grade on the quiz every week. Gee, I wonder how that happened. When you get to the end of the course, they're going to have the same quiz average. If every individual grade was the same, and it's the same principle here, if that's always equal to that, they'll be equal, the averages will be equal. A root mean square is a kind of average. And so the effective voltage and current obey Ohm's law. And so, you know, if you know how many ohms you got and you know you're applying 120 volts, you can figure out how many amps will be the result. The other question I want to address for each of these three things, resistors, capacitors, and inductors, is this issue of the phase difference. In a resistor, the phase difference is zero, again, because of Ohm's law, okay? The instantaneous voltage equals the instantaneous current times the resistance, which is just a constant. So if this gets twice as big, that has to get twice as big. If this gets 3 times smaller, that gets 3 times smaller. Whatever this does, this has to do the same thing in order for them to stay equal to each other. And so when this maxes out, this maxes out. When this goes through zero, this goes through zero. They rise and fall together. The voltage and the current are in phase. Let's see. I said something here about plus and minus signs. Actually, this already came up in an earlier example I did. I think it was in section. It might have even been at the tail end of section 6. Yeah, I think it was at the end of section 6, not in section 7. When you say V equals IR, you're saying that a voltage opposing a current is positive. When you write this, you're saying that a voltage opposing the current is negative. So, you know, doesn't really matter which way you do it, but you got to be consistent. And the way all the rest of this is set up, we're going to do it based on V equals IR rather than V equals negative I times R. If you're going to do that, you got to lose the minus sign out of Faraday's law and things like this that follow from Faraday's law. And so with that in mind, let's analyze what's going on in an inductor. So inductors. The voltage across, now we're assuming a pure inductance here. Realistically, the wire that's been wound up to make a coil will have some internal resistance, probably 10 or 20 ohms or something like that, depending on how fine the wire is. But in textbooks, you can magically make that go away by saying, assume a pure inductor with no internal resistance. And that's what we're going to do here. So in that case, the voltage across this coil is its self-induced voltage from Faraday's law. In the real world, there would also be a voltage because of Ohm's law. In fact, that's the point of that example that I was referring to a minute ago. The one I think was at the end of section 6. Oh wait, no, section 6. I'm thinking of the wrong course. In this course, it would be section 10. Yeah. So anyhow, hopefully you remember me going over that a couple of weeks ago, whatever unit of the course that was. Realistically, Ohm's law plus Faraday's law is the total voltage across the inductor. We assume no resistance, and the voltage across the inductor is just equal to L times di dt, where, like it says on the previous page, I equals the maximum current, the amplitude of the current, times the sine of omega t. So let's put that in there. The EMF is the inductance times, well, the derivative of this, this coefficient here is just a constant, so you just recopy that. And then the derivative of sine is cosine. And then it's the chain rule. It's not just the sine of t, because it's the sine of omega t. You have to take the derivative of what's inside those parentheses there. Because of the chain rule, there's also this factor of omega. And so let's just kind of move that out front so I've got all the constants collected together, which is a nice, neat way of doing things. And let's just play with the notation. Instead of calling it E for EMF, let's just call it delta V. As in voltage across the inductor. So call it delta V instead of E, and the voltage as a function of time across this coil is omega L times I max times the cosine of omega t. Well, I had same two questions as for a resistor. What plays the role of Ohm's law and tells me how many amps flow when I apply a certain number of volts? That question is going to be answered by this factor. And what's the phase relationship? That's going to be answered by this factor here. So let's just kind of do a split screen kind of thing. And we'll look at this first of all. The biggest that the cosine ever gets is 1. So therefore, that the biggest the voltage ever gets is 1 times omega Li max. So this thing that these three things multiplied together there, that is the maximum voltage. That's what the voltage equals when the cosine maxes out. So delta V max equals omega L times I max. I'm getting that from there. Well, let's talk about RMS because that's what people usually do. I'll stick a square root of 2 underneath both sides. And again, I'm going to abbreviate the abbreviation and just put an M for max. So Ohm's law says volts equals something measured in ohms times amps. And this time, when it's an inductor, the something measured in ohms equals omega times L. Let's give that a name. Seems like that's something we're going to want to talk about from time to time. What do you think? Inductive reactance sounds kind of catchy, doesn't it? Let's define inductive reactance. Inductive reactance. The usual symbol is the letter X with an L subscript. It's equal to omega times L. And you can see from this that it would be measured in volts per amp, which is better known as an ohm. And so substituting that in there, I've got delta V equals I times XL, just like V equals I times R if it was a resistor. Now, here I was talking about, with the square roots underneath, I was talking about RMS, the effective voltage and current. But if you don't divide by the square root of 2, notice the maximum voltage and current obey the same relationship. It's delta V max equals XL times I max. You stick the square root of 2 under it, and it's delta V RMS equals XL times RMS. So this works either way, effective or peak. It's just, like goes with like. If this is RMS, that one's RMS. If this is maximum, that's maximum. Maybe I should, no, I guess I don't need to write that down. As for the phase difference, well, the current is a sine. The voltage is a cosine. Let's draw some sketches to get a better look at that. But clearly there's a 90-degree phase difference here, sine compared to cosine. If I do the voltage as a function of time, that's a cosine. So that's going to look something like this. If I do the current as a function of time, these little times that I'm marking here, this is supposed to be the same time as that. This is supposed to be the same time as that, and so on. It says over here, the current is a sine. So that's going to look like this. Voltage leads. The current by 1/4 of a cycle. Quarter of a cycle, in other words, 90 degrees. So that's the phase relationship for this thing. So in a resistor, the phase angle is 0 degrees. For an inductor, the phase, remember back here at the very beginning, there was that phase angle right there. The phase difference between current, where I've built in a phase angle of 0, and voltage. If it's an inductor you're talking about, that phase angle is 1/4 of a cycle, 90 degrees. And a little more specifically, the voltage leads, the current lags, by which I mean whatever happens, the voltage does it first. At t equals 0, the voltage is at a peak. The current reaches a peak 1/4 of a cycle later. Voltage did it first, current did it later. Voltage leads, current lags. Or any other point along the graph, like right here, where the voltage goes down through 0. The voltage does that 1/4 of a cycle into the picture. The current goes down through 0, half a cycle from the origin. Okay, again, voltage did it first, current did it later. So voltage leads, current lags. And this right about here is probably a good place to leave off. That would be a typical class period length for the lecture, more or less. But just to give you a sneak preview of what's coming next, because I know you're all on the edge of your seats, when we get to capacitors, it's going to be kind of sort of like the same story. Once again, you're going to have volts equals current times a capacitive reactance. And once again, there's going to be a 90-degree phase difference, but it'll be the other way around. With a capacitor, the current leads and the voltage lags. And that's all for now. Over and out.